So today we're going to focus on the graphs and the domains of these functions. We're going to do a little bit of the notes. We're going to do a little bit of the homework. So look at number 5 with me. It says logarithmic functions are the inverses of basic exponential functions of the form y equals b to the x. That is, both functions show the same relationships between two quantities, but the input and output quantities are switched. The graph of f of x equals log base 4 of x is given. So that's what this graph is. Plot the points when x is 1/2, 1, 4, and 16. So let's make a little chart over here on the side. And they want us to plug in 1/2, 1, 4, and 16. Now remember, our function is the log base 4 of x. So we're going to be relating it to a power of on a 4, okay? So the first one's a little strange. So I want to start with 1, 4, and 16. Then we'll come back to the 1/2, okay? So the first one here, what power would we put on a 4 to get the number 1? So that's really the answer to that question. What power would we put on a 4 to get a 1? Well, the power we use on anything to get a 1 is 0. So the answer to that is 0. Okay. Now let's move to 4. What power would we put on a 4 to keep it a 4? Well, 4 is 4 to the first. If you want to keep it the same, your power you're going to use is 1. So that's 1. Then we have what power do we put on a 4 to get 16? So hopefully you recognize, since 16 is 4 squared, that our power we're looking for is 2. Now I want to move back then to that 1/2 power because it's kind of a strange one. So first off, we're looking for what power we would put on a 4 to turn it into the fraction 1/2. So that's a very strange thing to do. Now if it was 1/4, you would just take a -1 power, it would flip it. So negatives are going to be the thing that's going to help us. Also, you can think about the fact that if I want to make 4, put a power on a 4 to make it a 2 instead of a 4, I have to take the square root of it. So that's why the answer to this, I need a negative to flip it. I need a 1/2 power so that I can take the square root of 4. And so you would need a power of -1/2. Now what that means is that 4 to the -1/2 power should give us an answer of 1/2. Now let me show you why it does. The negative portion of it flips it. The 1/2 power takes the square root of it. The square root of 4 is 2. We do get 1/2 if we put a -1/2 on a 4. So that's how that comes about. But it really is an odd way of thinking about it. Now they want us to put those, like really plot those points on our graph. I know that when I made this into a PDF, see how the graph paper got split weird? So do your best to find those points. But let's go ahead and do that. At 1/2, we are down at -1/2. At 1, we are at 0. At 4, we are at 1. At 16, we are at 2. Now, this function has what is referred to as a vertical asymptote. What a vertical asymptote does, a vertical asymptote takes, and it is a line that we never ever cross, but we get super close to. So this particular function, because we have no transformations just in it left and right or up and down, this particular function has a vertical asymptote. So I usually just abbreviate that VA for vertical asymptote. It has a vertical asymptote at x equals 0. It will never touch 0, but it will get close to the vertical line, x equals 0. Now, our exponential functions always have a horizontal asymptote. So if you flip the x's and y's, that's why our logarithmic function has a vertical asymptote. Okay. Now, the last thing I want to do of the investigation today is part B. It says determine the average rate of change of y with respect to x as x increases from 2 to 5. So let's do that. Now remember, it's going to be delta y over delta x, or f of x2 minus f of x1 over x2 minus x1. So we're going to start with 5 and 2, okay? So that's f of 5 minus f of 2 over 5 minus 2. Now, 2 we could get an exact value for. The square root of 4 is 2, so we would need a 1/2 power. So the point at 2 is 2 1/2. So that one's a nice point. But 5 is not related to a log base 4. 5, we don't have a way of putting log base 4 into our calculator at this time. So for the 5, let's go over to our graph and let's guesstimate where that hits. And I'm going to guesstimate just because I have the answers. It's around 1.16. So the f of 5 is 1.16. The f of 2 is 1/2 over 5 minus 2. 1.16 minus 0.5 is 0.66. And then divided by 3 is 0.22. Okay. Now, I'm not worried about doing this one. It's the same procedure. Just remember, an average rate of change is just the slope if I were to connect those points. So what do I mean by that? Well, if I were to connect this point and this point, it is the slope of that particular line, okay? So that's what the average rate of change should be between those 2 points. So that's kind of what that is, okay? Now, I know you don't have an extra page at this time in your notes. Did I include this? Is that in there? So could you please add a little extra page for me? I want to talk about the graphs of our exponentials and of our logarithmic functions. So we're going to start with our exponentials. So if we have a function like our first one here, f of x equals a times b to the x, and b is greater than 1. I'm just going to give you a function that fits that category. Okay. This function always has a vertical asymptote. No, I'm sorry, a horizontal asymptote, which I will call HA, at a value of y equals 0. So could we first, along our x-axis, could you please put a little dashed line? Well, it's hard to see, but let me make it a different color. Anyway, there's a little dashed line right there. That is part of the graph we will never touch, we will never cross, we will never do anything. Okay. Now, for exponential functions, the domain is all real numbers. There are no restrictions on what I can or cannot put into this function. So when if I were the student, yes. So if I were the student and I was trying to do this, you can plug in whatever the heck you want. I usually will plug in 1, 0, and -1. So I usually plug in for these, just as long as it hasn't been changed left to right, I usually will plug in negative 1, 0, and 1. Now, those are the powers on a 2. I chose 2 this time. Those are the powers on a 2. If you take 2 to the negative 1 power, I get 1/2. 2 to the 0 is 1. 2 to the first is 2. So let me put some little marks here. And let's go ahead and graph our function. At negative 1, I'm at 1/2. At 0, I'm at 1. At 1, I'm at 2. So the graph is going uphill constantly. It is a growth. It is a growth. So it never ever goes below 0. It will always increase as we go from left to right without stopping. It is always an increasing function. So that's an example of a growth. Now I want to give you an example of a decay. So let's go ahead and graph 1/2 to the x. We want our base to be a number between 0 and 1. So proper fractions are good to deal with. So let's make that 1/2. Again, we do have a horizontal asymptote at 0. So let's go ahead and put that on our graph. We never cross that line. Okay. Again, this time I still would plug in negative 1, 0, and 1. I can plug in anything, but those are usually a good rule of thumb for an exponential function. Just plug in negative 1, 0, and 1. If you take 1/2 a fraction to a negative 1 power, it just takes the reciprocal of that fraction. 1/2 to the negative 1 power is going to be 2 over 1, or 2. Anything to the 0 power is 1. Anything to the first power is just that thing. Okay. So now we have a set of points that we can go ahead and put on our graph paper. So let's do that. At negative 1, I'm up at 2. At 0, I'm at 1. At 1, I am at 1/2. A decay is going to be ever decreasing. The one end is going to go up to infinity. The other end is going to go up, down toward that asymptote. It's never going to cross it, but it's going to go down and get as close as it can. Do you have a question? Anybody has any questions? Okay, so that's what an exponential graph looks like. Yes?
Sorry, I was trying to get the page copied, so I was trying to get it into the notes.
That's okay. What's up?
What is the H next to the Y?
So this means horizontal asymptote. So again, if you missed that, that's the abbreviation I will use for horizontal asymptote. So HA, I'm just going to call that a horizontal asymptote. So it is a horizontal line that a part of our graph skims across but never touches. Okay, so that is what our exponentials look like. Okay, so now if we, and this domain is still negative infinity to positive infinity. So that's what our exponentials look like. So now we need to now focus on our logarithmic functions. They're harder to graph. I wouldn't say they're harder to graph. They're very similar. It's harder to choose the correct x's to plug in. We don't have the leeway to just plug in anything we want, okay? That being said, now let's look at the logarithms you see here. The first one is related to our growth. So it is the inverse of a growth function. So let's call it the log base 2 of x. So that would be an example of what I'm talking about when the b is bigger than 1. So the log base 2 of x. These all have vertical asymptotes. Which I will abbreviate VA. And they all have, unless the function has a transformation or something where it's been shifted, it will always happen when x is equal to 0. So the first thing I'm going to do on my graph paper is I am going to put in a dashed line down the y-axis. And let's do it for both. They'll both have that. So we can say that both of them have a vertical asymptote at x equals 0. So it has a little barrier where the other one had an asymptote across the x-axis. These ones, if they flip the x's and y's, you should expect that it has a vertical asymptote down the y-axis. So it kind of hopefully makes sense. The problem with these is choosing correct x's because we don't have a calculator button for a log base 2 or a, we don't have a button unless it's a log base 10 or a log base e, the log or the natural log. So we don't have a button on the calculator, so we have to be very precise in what we choose. We have to choose numbers related to 2. So this is what I always choose. I first think in my head, what is 2 to the negative 1 power? Oh, that's 1/2. So what power did I put on that 2 in my brain to get 1/2? Oh, I put in negative 1. See that point earlier that we had? We had the point negative 1 1/2. It became the point 1/2 negative 1. Then I put in my head, oh, what is 2 to the 0? Oh, 2 to the 0 is 1. What power did I just use? Oh, I used 0. Okay, now what is 2 to the first? Oh, that's 2. What power did I just use? I used 1. Do you see how our x's and our y's reversed from the last one? So you have to be very, very mindful as to what x's you plug in so that you get out negative 1, 0, and 1. So now we're ready to graph this. Okay, so I'm just counting by ones here. At 1/2, I am down at negative 1. At 1, I'm hitting 0. At 2, I'm at 1. So this time our graph skims down here, but then keeps going up. So that is what a logarithmic graph looks like. And you can see it kind of think about if you did a little flip of this one, you do get this one. They are completely related. What has happened is the x's and y's have flipped positions. The x's and y's have flipped positions. So now let's do one where our b is between 0 and 1. So let's do the log base 1/2 of x so that it kind of matches the one above it. So think in your head, if I put a negative 1 power on a 1/2, what happens to it? It flips it. So that becomes a 2. What power did I just use? Negative 1. Okay, let's put a 1/2 power to the 0. I get 1. What power did I just use? 0. Remember, the answer to a logarithm is a power. And then let's think, what is 1/2 to the first? It's 1/2. What power did I just use? 1. So the same exact points we used earlier have been reversed. The x became the y became the x. So now let's go ahead and plot those. So if we go ahead and plot those, let's go. So we got 2, negative 1. 1 is at 0. 1/2 is at 1. It is still decreasing from left to right, but it skims across our vertical asymptote differently. It skims across our vertical asymptote differently. The left side goes down and then up. The right side goes up, then down. Okay, because one is related to a growth and one is related to a decay. The domain for both of these, if you wrote it as an inequality, x has to be greater than 0. But let's put that in interval notation. We can never hit 0. We get super close to 0. So we say almost 0 to infinity. Almost 0 to infinity. So we have what's called a restricted domain for these. We have what's called a restricted domain for these. Okay? So longs, I think the hardest part is determining what things to plug in. And you always want to make it related to, if I put this power on, what do I get? So then you know the y that you should get out. Because I put the power on it. The answer to the logarithm is power. And so if you think like that, that's how you can graph them. Okay. Next, go into Google Classroom for me. There is a 4.8 worksheet number 1. Please open up 4.8 worksheet number 1 at this time. And you don't turn in your 4.8 investigation. We're not done yet. We'll finish it tomorrow. Open up, go into Google Classroom. The 4.8 worksheet number 1 should look like what you see up on the board.
I was just wondering what's under this one.
It just keeps going down, down, down.
Oh.
Yeah. Okay, so worksheet number 1 is about some graphing, okay? Now, the worksheet number 2, we did look at a little bit yesterday, but we have to continue that tomorrow. These worksheets are your responsibility to finish it. We're going to do half of them together, and then it's your homework to do the other half. What I want to do is I want to talk about, so the first 2 are exponentials. The last 2 are logarithms, okay? So let's do one of our exponentials, okay? I want to do number 2 together. Now, I have chosen for you some really, I've chosen to get you started in these, the x's that are good to plug in, okay? And if you see an e, we have to use a calculator. E is approximately 2.71828. So we're going to have to use a calculator here. So let's go ahead and plug those values in so we have some plots, things that we can plot, okay? So we would do e to the -1 power first. We would get an answer and then multiply by 5 if we follow order of operations. I'm going to go to the nearest 10th. We can't really graph even hardly that accurately, but we'll try. This is 1.8. 5 times e to the -1 is 1.8. 5 times e to the 0 is 5 times 1, or 5. And 5 times e to the first is 5 times that 2.71828. It's approximately 13.6. Okay. Now, these have horizontal asymptotes. The x has not changed. If the x said x plus 1, x minus 2, x minus 3, 2x, that could affect that horizontal asymptote. For now, our horizontal asymptote is just y equals 0. So if we could, please, let's put a dashed line at y equals 0. So both number 1 and number 2 have an equation of the horizontal asymptote, which is y equals 0. Okay, now let's plot our points. Now, this is a growth. At -1, I am up to 1.8. Just guesstimate for me. At 0, I'm at 5. Now, at 1, I'm off the charts. So we're just going to swoop it way, way up, okay? So what do we know? Well, we have to head toward this asymptote. And we're going way, way up, okay? That's the graph. So please, it is your responsibility to do number 1 exponential, okay? So that's what number 2 looks like. Now, could we please do a logarithm together? I want to do, well, let's just do number 3, okay? For number 3, these are logarithmic equations which have a vertical asymptote at x equals 0. So the first thing I want you to put on your graph paper, please, is a dashed line down the y-axis. Okay. Now, if you don't see an index, you can use a calculator, but let's put a little 10 there, because that's what it is. And remember, the answer to a logarithm is a power. So let's evaluate 1/10. What power do we put on a 10 to get 1/10? Well, that would be the power that would flip it. What is the power that would flip it but not change it? -1. So this would be, don't forget the 2 in front, this would be 2 times -1 or -2. Now let's go to number 1, or plug in 1, okay? That is really saying, what power do I put on a 10 to change it to the number 1? What power do you put on a 10 to change it to 1? 0. So this is going to be 2 times 0, or 0. And then our last one, we're plugging in 10. So this part is really saying, what power do I put on a 10 to keep it a 10? 1, right? So this is 1. So this is 2 times 1, or 2. So now we have our points that are ready to plot, okay? 1/10, it's going to be really hard to get as accurate to 1/10. So just get close to 0 without touching 0 if you can. So over here at 1/10, we are down at 2. See how I'm close to it, but I didn't really touch it. I don't know how to get closer than that. Okay. And then at 1, I'm at 0. And then at 10, I am at 2. We should expect that our logarithmic function skims that and either goes up, 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 or down, 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 down. This is related to a base 10, which is bigger than 1, so we should expect that it goes up. So it is your responsibility to do the same thing for me, please, for number 4, okay? So that is just 2 more problems, and then you're good to go, okay? So just 2 more of those. Now at this time, do we have any questions on our graphs before we move into iMath? Do we have any questions on our graphs? Okay. Now at this time, could you go into iMath? Could you open up homework 4.8? We're going to do this homework together. Now I'm going to split screen it so that I have some like paper to work on. Okay, so if you want to do the same, that might be a good idea. Please open up, go into iMath. It would be on Sunday, the 20th. It would be on Sunday, the 20th. Go to the homework 4.8 domains and graphs. We're going to work on this together at this time. Okay. Now, question number 1, again, if my questions and your questions are a little different, adjusted accordingly. But it says, determine the domain of the natural log of x minus 6. So do we see how the natural log of x minus 6 has that x minus 6 there? On the ones we had done in the notes, it just was a plain old x, and I said that if our base was bigger than 1, that it's always x is greater than 0. When it has an inside junk like this, just put the inside greater than 0. So our inside is x minus 6. So we're going to take, where is x minus 6 greater than 0? And we're going to solve that inequality. So that means we are going to have a graph where x is greater than 6, okay? if you pulled up Desmos, there would be a asymptote at 6, and our graph would be scooched to the right 6 units, okay? So when we talk about domain, I would assume they want interval notation. So we want everything from 6 to infinity. Please make sure you're using parentheses on both the 6 and the infinity. So let me see if iMath likes that. Oh, it changed it. Like, go back. I didn't want it to be that. Oh my. Just a second. Oh, let's see. Good, 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 good. They want interval, good. They must have timed out for me. Okay, so mine changed to x plus 2. So x plus 2 is greater than 0 when x is greater than -2. So it goes from -2 to infinity. So please put interval notation. It will always end up flipping signs. Okay, so that should be the answer there. Okay, now where is the vertical asymptote? The vertical asymptote is always where the inside equals 0. So just set x plus 2 equal to 0 and solve it for x. In this case, it has been shifted to -2 for me. So in this case, it's where x is -2. You just set the inside of your thing equal to 0. Mine's at -2. Really? That's good then. Okay. That's silly, but okay. So set your inside equal to 0. Sorry. They have this new thing where the eraser shuts off, and if you lift your pencil, it drives me crazy a little bit. Okay. I know, I did once, and then it reset itself. I'll have to go back and change it. Okay. So now it says determine the roots. The roots of the function is where will the function itself equal 0. So to see where it says determine the roots. The roots is where the function itself is equal to 0. Remember, 0 is a power. Remember, it's a power. So if we wrote this in exponential form, we say where is x plus 2 is e to a power of 0. So if we switch it from exponential or from logarithmic to exponential, that's how we're going to solve it. What's anything to the 0 power? What's anything to the 0 power? 1, right? So really, you just have to set the inside equal to 1. It's always going to get you what you want. So where is x plus 2 equal to 1? And so that is going to be, if I subtract 2 from both sides, that will be at -1. You can also pull up the graph in Desmos. Where does it hit the x-axis? Remember, it may not hit the y-axis. It might, but you can find that point where it hits the x-axis. And then it says determine the x-coordinate when y is equal to 1. So when y is equal to 1, we're just going to set this equal to 1. Okay, because the whole thing is the y. The whole equation is the y set equal to 1. So let's do the same thing we did before. X plus 2 equals e to the first. So x equals e to the first minus 2. So I'm just going to put e minus 2 in there. I don't know. let's just submit this so we can make sure it's all lovely. Okay, now we get to the beautiful graph. So let's think about some things we know, okay? We know that there is a vertical asymptote at, for me, at -2. So I'm going to go over, and the first thing they want you to put on the graph is the asymptote. Mine's at -2. Remember, that's where the inside is equal to 0. So mine was x plus 2 equals 0 at -2. So I put that on first. Now we've got some good points here. This one here, I know that this is the point -1, 0. The y was 0, the x was -1. So let's put that on there at, let's find the point -1, 0. Just a second here. Okay, and now we need one other point. Okay, we need one other point. This is one where you can use a calculator. Remember, our function is the natural log of x plus 2. Let's plug in 2. So that would be the natural log of 4. So if you go into your calculator, you actually get to use a button for a change. The natural log of 4, we don't have to be careful about a natural log. You can plug in a number. So the natural log of 4, let me tell you that is approximately 1.4. Okay, so we're going to go over to 2. We're going to try to pinpoint where 1.4 is. You're going to not like that at all. That's a little better. Oh, and let's see if they like that. Yeah, so there you go, okay. Oh, let's do this one. I didn't realize the last one was a natural log. This one might be a log base 6, a log base 2, a log base 7. It is different as far as how you can enter it into a calculator. You can't, really. So let's actually do question 2. And I'm going to do it over here on the side so you can see it, okay? Okay, so the domain, again, just set your inside greater than 0. Whatever your inside is, you're going to solve. For me, it's from -5 to infinity. The vertical asymptote is when x plus 5 equals 0, so that's at -5. The root is where x plus 5 equals 1. So just set x plus 5 equal to 1. And so that would be, for me, -4. And when is the, what's the x coordinate when y equals 1? So what you get is for me, I get the log base 2 of x plus 5 equals 1. So I get x plus 5 equals my base to the first power. So in my case, it's just where does x plus 5 equals 2. If your base is 6, it would be where would x plus 5 equal 6, whatever it happens to be. And you just solve, and this is at -3. Now, on your graph, you put on your vertical asymptote. Remember, mine was at -5. Then I know it hits the x-axis. That's not -5, is it? -5. We know it hits the x-axis at -4. I know it at 1, it is at, or at -3, it is at 1. And so then we should be done. I just totally didn't hit the points I should have, but okay. Let me see, are any of them weirder than that? And we can maybe do a few more together tomorrow. Okay? So we'll practice more tomorrow.